Our next speaker is Zhongshuang Yuan, full professor from Shandong University, and will speak on likelihood-based Mendelian randomization analysis with automated instrument selection and horizontal pleiotropic modeling.
Okay, so thanks for the nice introduction, and thanks for the committee to give me this opportunity for the presentation. And today I want to going to talk about on the likelihood-based Mendelian randomization method is our recent work. And thanks for Professor Jia's nice introduction for the MR. So I will give here I will give a brief introduction for the Mendelian randomization. Mendelian randomization in terms of MR is a powerful statistical tool to perform a causal inference in genome-wide association studies. And it tries to investigate the causal effects of exposure traits on a complex outcome trait. So MR is a special form of instrumental variable analysis, which have been widely used in other domains. Now, in this particular case, we treat SNPs as the instruments. So, for example, in epidemiology studies, one may be interested in to investigate the causal relationship between the exposure smoking and the outcome BMI. So, most of the MR are mainly focused on two sample MR setting. That is, we have the exposure GWAS data from one sample, and we got another independent sample for the outcome GWAS data. So the goal is to infer the causal effects of the exposure on the outcome. Here, we use the parameter alpha here. And because the data is from two different samples, if we want to link the exposure and the outcome, we will use the common set of SNPs. Here, the SNPs are the candidate instruments. So for now, there are many MR methods because the public GWAS summary statistics are available. And most of the MR methods rely on select a set of independent SNPs to serve as instruments. Usually, the common procedure is through the LD clumping. However, in genetic field, the LD clumping usually to choose the tag SNPs, not the causally related ones. So indeed, in the GWAS file mapping field, many researchers suggest to use a probabilistic modeling to select the best causal ones. So LD clumping may be suboptimal. And another question is that most MR methods mainly focus on the independent SNPs. As we all know that many multiple SNPs are local in high LD in the local region of the cosmos. So only using independent SNPs may only capture a small fraction of exposure variance and may lose loss of power. So that's the one issue. And another issue to maybe make the MR complicated is that the two types of pleiotropic. Those SNPs can affect the outcome, not through the exposure. So if the SNPs on the exposure, the effect size of SNPs on the exposure and the effect size of SNPs on the outcome are not correlated, we call it uncorrelated horizontal pleiotropic. That is, the SNP may have a direct effect on the outcome. And there are another type of pleiotropic, just as Professor Jia mentioned, that is correlated pleiotropic. That means that SNPs can also affect the unmeasured confounders, which both affect the exposure and outcome. So in this case, the effect size of SNPs on the exposure and the SNP effects on the outcome are correlated. So we term it correlated horizontal pleiotropic. So because in MR, we only focus on the causal path. So it is very important to control for and test the modeling both type of horizontal pleiotropic. So motivated by these limitations, we developed MRID. It terms MR with automatic instrumental determination. In MRID, we want to do two things. One is to select the true valid instrumental SNPs. Another is to control for the two types of horizontal pleiotropic. So here is the two sample MR basic framework. So we also have two GWAS data. In the exposure GWAS data, we link the exposure with the SNPs using the equation 1, where X here is the exposure, and the X is usually often the N by P matrix for the SNP genotypes. Again, the P SNPs are often correlated. And the parameter beta is the SNP effect size on the exposure, where we want to select the true valid SNPs. And the initial X is the error term. So this is the equation 1 for the exposure GWAS. But in the outcome GWAS, we don't have the exposure. We did not get the altitude, but we can write the same equation in equation 2. There's a link the altitude with the genotypes, where we denote dy as the genotype matrix in the outcome GWAS. And then in equation 3, we decompose the trait y into the causal effect and the two types of horizontal pleiotropic effects. And here, alpha is the causal effect that we want to test and estimate. And 8.0 and 8.1 are two types of horizontal pleiotropic effects. So this is our modeling framework. So under this model, we would like to make some model assumptions. So the first goal is to make the selection. So to enable the automatic instrumental selection, we specify a sparsity inducing prior on the instrumental effects on the exposure. Just as Professor Zhu's comments on the morning's MR talk, that's give one SNP. How do we know it is a valid SNP, valid instrumental SNP? Here, we want to give some probability to indicate whether this SNP has some probability to be a valid instrument. So we specify a sparsity inducing prior on the instrumental effects on the exposure. So this is a common modeling assumption in the variable selection field. That it means that with the probability pair bit, the SNP has effect where it's following normal distribution with the mean 0 and the variance is sigma beta square. And with the probability 1 minus pair bit is not have not effect. So for modeling horizontal pleiotrope, we model it depending on whether the SNP is a valid or non-valid instrument. For select SNP instruments, that is the beta does not equal to 0, we assume they have exhibit two types of horizontal pleiotropy. One is the correlated. That means for this SNP, it has a probability pair C have the correlated pleiotropy effect. Because in this case, the correlated pleiotropy, the SNP effect size on the exposure and the SNP size on the outcome are correlated. We assume the correlation coefficient is rho. So that means that the correlated pleiotropy is equal to rho beta j here. And with the probability 1 minus pi c, that has no correlated pleiotropy. So for the uncorrelated pleiotropy, for SNP, we also use the normal distribution with the probability pi 1. So for SNPs that are not selected to serve as an instrument, we also model to improve the model efficiency. And we assume they may exhibit uncorrelated pleiotropy effects, usually use the same distribution. So this is the simple schematic. So we get a set of a branch of p-correlated SNPs that's correlated in the crossmode. So we first, to make the selection, we divided these p SNPs into two parts. One is SNP set 1, that's the true causal effect. Another is SNP set 2. So for this set SNP, for SNP in SNP set 1, we also distribute three causal paths. One is the causal path, another is a correlated causal path, correlated pleiotropy. The remaining one is the uncorrelated pleiotropy. And for the SNP in SNP set 2, we also modeling because we want to improve the efficiency. So under this modeling framework, and we developed an inference algorithm. We developed an approximate inference algorithm and the maximum likelihood framework using either individual level data or summary statistics. So the algorithm is based on the observation that the likelihood function of the causal effect alpha is a ratio between the posterior and the prior. Because the posterior is asymptotically normal, so if with a normal prior assumption, we can obtain the approximate maximum likelihood estimate alpha hat, and it's derived the standard error of the causal effect based on the posterior summaries. So if so, we can use the word test to test whether the causal effect is 0 or not. So to assess the model performance, we conduct simulations. So we randomly select 60,000 individuals from the UK buyback. We split it into two equal size sets. 30,000 is the exposure GWAS, and the remaining is the outcome GWAS. So this is a two sample MR setting. We use many SNPs from chromosome 1, and we simulated the exposure and the outcome and now scenarios. That means there's no causal effect. And the alternative scenarios, that is, there's some causal effect. And we conduct simulations under the model assumption and under the model misspecification. And we also consider the pleiotropic. So we conduct several simulations to consider in the absence of horizontal pleiotropic, in the presence of both, or in the presence of either one. So we also compared Marid with several methods. It is the four versions, including the four variants of IVW, and it is the random effect variant, the weighted model variant, the robust variant, and the weighted median variant. And we also compared with RAPS method. It is a profile score method. And so we also compared Marid with the two recently published MR mix method and cause method. So there are only two methods to which models boost the uncorrelated and correlated horizontal pleiotropic. However, these two methods rely on non-likelihood inference method, the inference method, and as we will show later, they are given uncalibrated p-values. So for the type one control, we here we want to see the different methods, the performance for the different type one control. So in the homogeneous setting, that means that the SNP effects on the outcome is from normal distribution. And for the heterogeneous setting, that means that the SNP effect size on the exposure is from a two mixed normal distribution. That means that there are some parts of SNP have large effects, and some parts of SNP have small effects. So in the two settings, we can see that Marid is the purple color. It means it says that in the homogeneous setting, the KQ plot is along the diagonal line. And we can see that the cause method is quite deflated, which is consistent with the simulation results in the previous cause paper. And for the MR mix method, in the homogeneous setting, MR mix shows good, well-calibrated p-values. But in the heterogeneous setting, the MR mix shows inflated p-values. That means that the MR mix are not robust to the distribution. So we also designed the simulation under the uncorrelated horizontal pleiotropic or under the both correlated both types of pleiotropic. So you can see that the Marid, the purple color is still have good behavior. That's not surprise because we clearly modeling the both types of pleiotropic. So for the power setting, we can see that the Marid method is the purple color shows the highest power. And no matter there's uncorrelated pleiotropic or correlated pleiotropic. So we also to investigate the effect size estimate from Marid method. You can see that no matter what is under the null and under the alternative setting, the estimates are unbiased, so reasonable. So for the real data application, so my big issue is that you never know the truth in real data analysis. So for the first real data analysis, we perform the treat on itself analysis. So in particular, we get the 300 individuals of European ancestry from UK biobank. And we also split into two equal sized sets. One is used in the exposure GWAS and another is used outcome GWAS. So in this case, we perform the treat on itself analysis. We mainly focus on 8 cardiovascular disease trees and examine the causal effect of each treat in the exposure GWAS on the same treat in the outcome GWAS. So in this case, it is expected that the true causal effect is exactly to 1. And we want to compare different methods that we can see that if whether different methods can give a causal effect that is unbiased. But because in this case, we know the true causal effect, we have compared different methods whether the confidence interval can cover the true value 1. So here is the results. So for these 8 treat pairs, treat itself on itself analysis, from this figure, we can see that Marid is the purple color for these 8 treats. Marid can have unbiased estimate, and the confidence interval can cover the true value 1. And there's another method that is also cover the true value. That's the cause method, is the blue color. But we can see that the confidence interval for cause method is quite large. This may be because the cause method uses non-likelihood based inference. So for other methods, for example, for the MR mix methods, is the black color, and there are some trees are covered in the true value, and some trees they are not covered. For example, in BMI and the LDL, the MR mix give unreasonable estimates. So for the real data application tool, we conduct the cause effect screening because one main advantage of MRID is to use the likelihood-based inference method. So they can give a calibrated p-value. So we can screen the causal risk factors for some disease. So in particular, we mainly focus on the exploratory 31 lifestyle risk factors. It's including 8 physical activity traits, 12 alcohol traits, 10 diet traits, and 8 smoking-related traits. And for the outcome traits, we mainly focus on the 11 cardiovascular disease-related traits, including 4 pulse wave traits, 2 blood pressure traits, 4 blood lipid traits, and BMI. So we first examined the 341 treated pairs for the exposure of the outcome effects. That means we treat the exposure trees as the exposure, and we treat the outcome trees as the outcome. And we also conduct the reverse analysis. That means that we treat the exposure trees as the outcome trees, and we treat the outcome trees as the exposure trees. So for the reverse analysis, you can see the number of treated pairs is 304. It is less than the 341. This is because there are no SNPs or no instruments that for some cardiovascular disease. So there are totally 645 treated pairs. So we run different methods to see their performance. So here is the real data results. The left panel, we can see the Q plot. That means the purple color is the MRID method. So first is along the diagonal line and then go up. So for other methods, for example, the RVWR and the MR mix, it's deviates the diagonal line very earlier. And so there may be some inflating. And for the cause method, it's at the beginning, it's deflating. So in order to further check whether there's the true phenomenon, and we permit the data, because using the permutation data, it is expected that there's no signal. So the right panel is for the QQ plot for the permutation data, and we can see that there's no signal for MRID method. So overall, in this causal treat pair analysis, MRID detected 8 causal treat pairs based on a Bufferoni correlated value threshold, of which have strong biological support. For example, MRID detected a negative causal effect of smoking on BMI, which is a well-known fact in epidemiology or in some biomedicine field. So I will give a brief summary here. So we developed MRID. It's an MR method that automatically selects the instrument while controlling for both uncorrelated and correlated horizontal pleiotropic. And MRID control for type 1 error and exhibits high power. This may be we use the likelihood-based method. And MRID is effective in various simulations and real data analysis, including treat on itself analysis and large-scale MR screening. So I want to acknowledge Professor Xiang Zhou is from the University of Michigan and Department of Biostatistics. This is my advisor when I was postdoc in UM Biostatistics. And Professor Fu Zhongxue is a group leader in Shandong University. Also, my many students who help to manage the data and the processing and to check some manuscripts. So this method has been published in Science, and the software are freely available at GitHub software. So that's all I have. Thanks.
Thank you. No need to ask about the software this time. Any other questions? Yes.
I just wondered, did you try and do anything with kind of consortium data for any of these things? Because actually, it might be useful to know how well your method works when you've got data from different cohorts that have been combined to sort of boost numbers. There might be sort of different levels of sort of pleiotropy going on within different cohorts, for example. I mean, so did you look at that?
Okay, this is a very good point. And so for the manuscript prepared, we just use the UK Biobank and using individual level data. And so when after the paper has been published, we received some emails and some comments on the software, and they want to use some consortium and using some summary statistics publicly available. And we have changed the code several times to make it more easiable to for different data sets. So because this is but I think it is really hard question because different data sets usually have different formats and different, different researchers can prepare their data using different formats, different data processing procedure, and so we want to change the code to user friendly. Okay, I see. Thank you. Thank you very much. This may be a good session. We may check the code using different. Okay, thank you.
I have a question as well. Any other before I sort of just set myself at front of the line? No. I was wondering, the automated part is, of course, it's extremely attractive. It can also almost be seductive. So how do you see it play together with more biological based thinking or design based thinking? So instead of picking the instrument automatically, you could say, oh, you should find the right negative control, you should talk to the biologist and so on. Well, how do you see those two paradigms support each other?
Okay, thank you very much. So here, I mean, the terminology automatically is just, I think it's something like the data adaptive. We never know for one SNP, we never know whether it's valid or non-valid instrument of SNPs. So we just to derive it, to estimate the probability from the data at hand. So it means the data adaptive. So for your question, to add some biological knowledge, we have discussed this in our discussing in our paper. So maybe as our further work.
Well, then please join me in thanking the speaker and indeed all the speakers of the session. After this, we'll have a 15 minutes break.
Thank you.